Alright guys, so in this video we're going to be looking at differential equations. We're going to have some goals within the 6.1 as a section at all. But we're going to be able to define differential equations. Our goal is to be able to solve a differential equation, including examples with discontinuity, and using the fundamental theorem to solve an initial value problem. Alright, for this video specifically, we are having a little mini goal of, can we define what a differential equation is? Can we solve a basic differential problem? And then the second example as well too that we're going to look into is a basic initial value problem as well too. Before we go any farther, let's talk about differential equations. Alright? Now if you get into higher level mathematics, you are going to take a class that is literally just called differential equations. It's all about this concept, right? For our honors calculus purposes, we are going to look a little bit more just skimming the top just a little bit, just to kind of see a little bit about what they are about and how they relate to some things that we've been doing in the past. So what is a differential equation? Simply put, it's an equation involving a derivative. Alright, it's called a differential equation. That's it. Alright, so it's an equation involving a derivative, plain and simple. Now, obviously, like I said, it goes a little bit more in depth than that, but we're not going to worry too much about it. There's an extra little caveat that I have along with there that you see the second part of the description. The order of a differential equation is the order of the highest derivative involved in the equation. Okay, the order of a differential equation is the order of the highest derivative involved in the equation. All right. So you may have a first derivative, you may have a function or an equation that involves a second derivative, and so on and so forth. And so just the order of a differential equation can be defined by the highest derivative involved. It's like as we were kind of talking about back in pre-calculus and the order of the degree of a polynomial function, right? The highest exponent, or the highest degree, is going to be what we classify it as. If it's to the squared, it's it's a quadratic. If it's cubed, it's cubic, and so on and so forth. That's our highest exponent that we are dealing with. And the same kind of goes for our differentials, all right? So let's take a look here on our first example. The goal of this first example is to look into simply solving a differential equation. All right. So directions will look at something like this. Find all the functions y that satisfy a derivative that equals secant squared x plus 2x plus 5. All right, let me say it one more time. We want to find a function y, or find all functions y, that will satisfy a derivative that equals secant squared x plus 5. Okay? So, when we're looking here, remember, this is the derivative, and it's basically asking us, well, what was the function for y that you took the derivative of with respect to x, all right, that's going to satisfy a derivative that equals, as you see on the screen right now, okay? Well, hopefully this is starting to look similar to a instruction that we've seen in the past. Because you're basically asking yourself, what was the step before, right? So I had a function y, I took the derivative of it, and I have secant squared x plus 2x plus 5. So what was a possible y function that arrived at this possible derivative? And hopefully you're starting to think of, well, this looks like an antiderivative type problem that we're really looking for in the end. Alright? So let's take a look here. So if I want to find possible function for y that's going to satisfy dy over dx equals secant squared x plus 2x plus 5, I just got to think about what that step before I took the derivative was. So in my case, the step before dy dx would be y. And then the antiderivative, or the step before secant squared, well, that's one of our trig function derivatives. The derivative of tangent is secant squared of x. And so really this was tangent of x beforehand. Well, now it says the antiderivative of 2x. Remember how we take our antiderivatives? You raise the power and divide by that power. So this becomes not 2x, Well, we're going to add one power to it and divide by that new power. So it will become x squared divided by 2, and those 2's will cancel on out, and they will just give us x squared. And then we've talked about the antiderivatives of a constant. With the antiderivative of a constant, just throw the x in there, or whatever variable with respects to that we are dealing with. Alright? So that is a possible for y. But remember, what if there happened to be a constant involved in this scenario? That's when we add our plus c. So remember, if we took the derivative of a constant, it would have been 0. So there's a possibility that there was a constant in there as well, too. Alright? So you might be thinking, oh, well, no, this isn't an exact equation because there is c that is involved. Well, yes, there is c going to be involved because it's find all the functions y that satisfy. All the functions are whatever plus c is. Maybe c was 0. Maybe c was 3,000. We don't really know what c was. So this is, I'm in agreement, this is a general equation that satisfies this derivative, but that's really all that we have. So this is a general solution to the differential equation. Okay, let me say that one more time. This is a general solution to the differential equation. Notice that we can't find a unique solution to a differential equation unless we are given further information. Okay? We can't take it that next step further unless we're given further information. If the general solution to a first order differential, so that means first derivative differential equation, is continuous, the only additional information really needed is the value of the function at a single point, right? So if we had the value of the function when x was some value and I knew what it was going to be, I can go ahead and find out what the value of c was. And when this happens, we call this an initial value problem. So let's say they give us a little bit more information, like in example 2. So it says now find the particular solution to the equation whose graph passes through the point 1, 0. Okay, and here's our derivative, first order, once again. So now we have to kind of think to ourselves, what's the difference between the last example and this example? The reason why I wanted to put these two in the same video is to compare them. The last example that we were looking into, the direction said find all the functions, all the possible c's, basically, right? And now in this one, we want to find the particular solution because they give us that little bit of additional information that is in there with the point 1, 0. So let's first off by finding the general solution to the problem. The general solution is just the antiderivative here. So the antiderivative of dy dx is just y. The antiderivative, or the step before we took the derivative of e to the x, remember, it's just e to the x. Derivative of e to the x is e to the x. And then for negative 6x squared, we're going to raise the power and then divide by that new power. So we're going to raise the power to 3, divide by that 3, and 6 divided by 3 will be 2. So it should be negative 2x to the third power. And then the general solution will just be to add that constant of c in there. But I have values for x and I have a value for y when x equals 1. That's what that through point 10 is going to mean for us. When x equals 1, I know that y equals 0. So let's find out what happens when x is 1 and y is 0. So 0 for y, substitute 1 in for x, and let's see what that constant actually was. Maybe it was 0, maybe it's got value to it. Let's take a look. So 0 equals e minus, well, 2 times 1, that's just going to be minus 2, plus c. I want to go ahead and find out what c is. Well, this is going to show me that if I add 2, and I subtract e, That's just going to be 2 minus e for a value of c. So I get it, 2 minus c has value, but it also has value by how it is right now, so I can leave it like that. And if I want to find the actual particular solution to it all, I can make the statement that the particular solution is y equals e to the x minus 2x cubed plus c, right? But c now has value. So really it's going to be plus 2 minus the e that we found, 2 minus e for c. Okay? So there is an example of one, we've defined differential equations. We've done an example in which we find a general solution. We've now done an example in which we have an initial value problem that gives us a particular solution specifically, right? So I want to give you guys a shot to do one on your own, all right? The directions will be to solve the initial value problem, all right, explicitly, or just kind of how we've been doing here, right? So what I would like you guys to give a shot at is the following. Let me kind of separate this from everything on else. Your first derivative, or the order of it is the first derivative, d of a over x is going to be equal to 10 times x to the 9th plus 5x to the 4th minus 2x and then plus 4. Alright? Your situation or your initial values is a equals 6 when x equals 1. So there's your scenario. Your answer that I'll go ahead and just give it to you so you can kind of check on your own. Your answer in the end should be a will equal x to the 10th plus x to the 5th minus x squared plus 4x plus 1. Double check and see if you got the exact same answer and if you're on board with that. And we'll go over it first thing on to the next one.